Constant acceleration is going to be our first big kind of approach that we're going to use to solve problems in this class. As we go throughout the semester, we will add on to our toolbox basically. So when we start talking about forces, we'll be looking at how do we use Newton's second law as kind of our overarching approach. Then we get into energy. We use conservation of energy as our foundation. And so early in the semester, really, we're focused on just constant acceleration type of problems. This is our strategy. It's our game plan for working with the problems that we are going to be faced with in this early part of the semester. So in this video, I'm going to just derive we have three starting equations that we use when we're working with constant acceleration. In each of our kind of big approaches, you'll be responsible for identifying a specific type of diagram, identifying and defining all of your relevant variables, and then also starting your solution with what I call a starting equation. And so in this video, I'm just going to show how we can derive each of those three starting equations from stuff that we've already been working with. So in constant acceleration, I'm just going to write here. So constant acceleration is a vector. In here, we're going to be focused on one directional motion. So I am going to use just variable A. I don't need to distinguish between A average or A instantaneous because our acceleration is constant. So I'm just going to use A as my variable. We're also going to have time is involved. So I'm going to use a T0 for my initial time. I'm going to use just a T for my final time. We're going to talk about positions, and I'm going to use S as just that generic position. So anywhere I put S, remember you could put in an X, or you could put in a Y, or you could put in a Z. I'm going to use that initial position. S is going to be S naught, and then my final position is S, and then we can have a velocity, initial velocity, and final velocity. So I'll just put up here. These are initial and final variables that we'll use. So as I said, there'll be three equations. I'm going to start with just the first one. So to get to the first one, we're going to use this relationship that we know that acceleration is just the derivative of our velocity. So if I start from here, I'm going to rearrange and just move that dt to the other side. So I'm going to have an a dt is equal to dv. We're going to integrate both sides. And on the left-hand side, I'm integrating with respect to dt. So I'm going to go from t naught. And actually, I'm going to even be more specific. So I'm going to go ahead and say that our initial t is 0. It just makes it a little less messy as I'm putting these bounds in here. So I'm going to go from t, we're going to take from 0 to whatever some final time is. My velocity, I'm going to go from v naught to a v. So I'm going to integrate both sides. A is that constant. I'm going to pull that out. So on the left-hand side, I just have an at. And on the right side, I'm just integrating dv, so I have a v minus a v naught. I'm going to rearrange this and just say v is equal to v naught plus a t. So this is one of our first, what I call starting equations for constant acceleration. The final velocity is going to be equal to that initial velocity plus the change in velocity. And change in velocity is essentially that acceleration times my time. Okay, so that's one of our equations. For our second equation, I'm going to use a similar approach. I'm going to just use our definition of v. So v is dx dt. So same thing, I'm just going to rearrange that a little bit, move the dt to the other side. So I'm going to have v dt equals dx. Then we're going to integrate both sides of this. Where I have the v there, so what I'm going to do here is just take this over here. So v is v naught plus at. I'm going to plug that in for my v here. So I'm going to integrate v naught plus at on this side. So all of that dt equals, we're going to integrate d, and I knew I was going to do this, so I said I was going to use s for the variable, and then I put x in there. So I'm going to switch these guys to s's. So here I have a ds. And if we think about our bounds, so here I'm going to go from s initial to an s final, and here I'm integrating with respect to time, so this is going to go from 0 to t. All right, on the left-hand side, I can just split that up. So I'm going to have integral v naught from 0 to t dt plus, we're going to integrate a t dt from 0 to t. And that is going to equal my integrate my ds from s naught to s. Okay, so each piece, we're just going to go through each of these. So in that first term, so V naught is just a constant. So this is just going to be V naught T. So V naught is the initial velocity. So that's something that is constant. In the second term, A is constant. I can pull that out. So I have A, then I'm going to have a T squared over 2. And then on the right-hand side, we're just integrating the S. So this is going to be S minus S naught. Similar to the first one, I'm just going to rearrange this here. So I'm going to say this is S equals S naught plus V naught T plus 1/2 A T squared. And so this is going to be our second equation. If you're looking at your equation sheet, you're going to find these are the equations that we'll see in our constant acceleration section. So I have one equation solving for a final velocity. This second equation here, the way I've written it is showing that our final position is equal to the initial position plus my changes in position, right? So these pieces here are going to give me my change in position. All right, so we have two equations. We're going to do one more. If we look at both of these equations, we can see they both have time in them. So I would like to have an equation that does not have time in it, so that if I'm working a problem and I don't have information about time, I can maybe solve for some of the other variables. So what we're going to do is combine these equations. So I'm going to solve this one. So we'll go first. I'm going to solve this one for t, and then plug that value of t in the next one, and we'll end up with a new relationship. So for number 3, so I'm going to go ahead and solve this guy up here for time. So time is v minus v naught over a. And then again, I'm going to take that and plug that into, I've got t in 2 places here for this one. So I'm going to go, I've got s equals, there'll be a lot of stuff to keep track of, so I'm just going to try to do this in pieces. So I've got a v naught times a t, and then this is the t we're plugging in. I'm going to throw that in there, plus a 1/2 a, and then this time I got a t squared. So v minus v naught over, not 2, v minus v naught over a. And that whole thing there then is going to be squared. Okay, so here I've got a lot of terms in there, so I'm just going to simplify this, right? So to make it a little bit cleaner to work with. So one of the things I'm going to do is I'll just talk through kind of the steps. If you want to take a little bit of time and work through this, is good just practice in algebra. I'm just going to talk through what I'm going to do and combine probably a couple of steps together. So I'm going to move this to the other side, and then I am going to, if I move that to the other side, I've got to divide by a and divide by a squared over here. So I'm going to multiply the whole thing by a. And then I'm going to also multiply the whole thing by 2 to get rid of that half there. So kind of in steps. So first up, I'm going to go s minus s naught. So that's over on that side. And then I'm going to divide everything by a. So that means there's going to be an a on this side. And that basically gets rid of that a. And it gets rid of one of these a's on the bottom, because this is an a squared on the bottom. And then I have this other a here. So by multiplying that a on the other side, I've essentially eliminated those. And then I'm also going to multiply by 2. So I'm going to put a 2 here. So if I multiply by 2, oops, that gets rid of my half here. But then I also need to multiply this term by a 2. So I'm going to put a 2 in here. And I've got a v naught. And so all I have left here now is a v minus v naught, because I multiplied everything by a, so that a on the bottom is gone. And then over here, I've got a v minus v naught. This whole thing is squared. All right, so I can still simplify on that right-hand side. So this is the same over here. On this side, I've got a 2v naught v minus a 2v naught plus a v squared minus 2v v naught plus a v naught squared. Okay, so let's see what we can combine here. I've got a 2v naught v minus a 2v naught v, so those guys cancel each other. I've got a minus 2v naught, and this v naught should be squared. So this v naught, the one that I just put the square in there, that came from this multiplied by this. So I've got a minus 2 v naught squared plus a v naught squared. So that gives me a 1 minus v naught, and I have a v. So we are almost to the point where we want to be here. So I've got a minus v naught squared plus a v squared. And then as I did with the previous ones, I'm going to just rearrange this. So I'm going to do v squared on this side. And then, so that means I'm moving this right to the other side. So I've got a v squared equals a v naught squared plus 2a. And then this s minus s0, that's my displacement piece. Okay, so this gets us to our third equation. So anytime we're working with constant acceleration, we're going to do our diagram, we're going to define our variables, and then we're going to say, okay, which equation are we going to pick from? And these are the three equations that we're going to pick from. If we set up our problem, define our 6 variables across our interval, then we can always just pick and choose one of these equations to work through, find the solution to whatever our problem is asking us to look for.